Hello, good afternoon. I think that many of you already know me, so there's no need for introduction. I've been doing this IPv6 stuff for a number of years. Tony and I were co-chairs of the NG Trans Working Group back in the 2000. And yes, we created a lot of transition technologies. The beauty of transition technologies is that there are many of them to choose from, which actually is a problem of transition technologies. There are just too many of them to choose from. So I think that Tony and I will have to apologize because we created too many of them. And one of the reasons was, at the time, we honestly, looking back, had no idea how this thing was going to play out. And maybe this time around we do have more ideas. So the thing about having been in this IPv6 world for so many years is that we have seen the things that work and the things that don't work, the ups and the downs. And I would like today to focus a little bit on those two transition technologies that Tony alluded at are seeing a lot of traction right now, especially among service providers. So classic stuff, legal statement, okay. We've talked about 6RD, DS-Lite. Essentially, those are the two things that I'm going to describe today. The idea of 6RD is to say, well, I have this v4 network. The edge of my network we access may or may not be able to go to v6. I may have a router there that can have some problems to go to v6. The core is easy. Usually there are fairly recent routers from any of your favorite vendors, and usually it goes to v6 very easily. It's a couple weeks project to do that. Getting your access ready is a much more difficult story in some cases. So if you have routers that can go to v6 natively, that may not be an issue. If you don't have those routers, then the choice that you have in front of you are fairly limited. Is about tunneling. So actually, I don't like this word tunneling. I better use another term, which is encapsulation. Tunneling can look scary because, yes, you can go to the other side of the planet before coming back. But if you look at tunneling as, this is simply about putting a header in front of another header. When you put an Ethernet header in front of an IP header, nobody worries about it. That's encapsulation. So if you put an IPv6 header behind an IPv4 header, or an IPv4 header behind an IPv6 header, it should be no different. The thing is about this being managed versus this being completely wild. If it is completely wild, then you will go on the other side of the planet, you go to unknown places, and well, if you go to unknown places and you have unexpected results, you should not be surprised. Now, if this is constrained and this is managed, and you go from one edge of your network to maybe 2 steps within your network, you know exactly where you go from and where you end to, then there should be no problem. So if it is about going from the CPE to a router that's just 2 hops away, you're not going to go across the planet twice. You're simply going to go 2 hops away. It's in the path. You may be introducing a couple milliseconds extra to go and decapsulate the packet, but that's about it. So this is what 6RD is all about, using this v4 infrastructure and creating v6 over v4. So as Dave Watt pointed out this morning, this usually comes with a NAT, because if you had enough IPv4 addresses to start with, why would you even care about IPv6? Your business is v4 today, so you would just stay with v4. Now, you don't have enough v4 addresses in the future, so you need to do something about it. So there's a NAT and there is v6. So it's better than having just NAT and IPv4. You have this escape route to IPv6. So that has been standardized in our software working group, and there's a number of products already out there to do that. It's very easy to deploy. All you have to do is to drop a 6RD relay. And it's essentially stateless, so those are fairly simple boxes. Now, there's a little caveat to it's easy to do. And the caveat is what is happening on the CPE. Because you need to have a CPE that can do IPv6 and a CPE that can do 6RD. So in the case of an operator like Free Telecom, it was relatively easy because they actually control what goes on the CPE. They build their own CPEs. They have a source code. So they were able to simply hack the source code, put whatever encapsulation was needed, tested, push it to all their customers overnight, and problem was solved. I'm not sure this applies to every single service provider on the planet. Most of them I know actually don't control the source code on the CPEs. So even though that's easy to deploy, it doesn't mean that this is going to get immediate deployment status, immediate traction, because you still need to modify those CPE. You need a new CPE. This actually is really the #1 problem that I hear service providers telling me about, changing those CPEs. Another thing that can be done is also dual stack. So if you are a large service provider and you have enough v4 addresses, and you want to also offer v6 because you've decided that it will be the right thing to do, when you can offer v4 and v6 at the same time. That does not solve your IPv4 exhaustion problem, because the prerequisite is to have enough v4 addresses to give to every customer. But if you are in this lucky situation, very fortunate situation, that's something that works. Still, a caveat to this is you need an IPv6 ready CPE. And if you have, I don't know, 5 million customers or 10 million customers, and each of them has a CPE that costs, I don't know, let's say $100, $100 times 10 million customers, it's a lot of money. Now, another alternative is the exact mirror image of 6RD, which is to say, service providers decide that there's a time before the exhaustion and a time after the exhaustion. Before that line in the sand, those were customers who had a v4 address. They have whatever CPE they had, and they're going to keep it. After this line in the sand, we're talking about new customers, and they want to build new networks with new equipment for new customers. So those are things that are being spec'd out now, and it's possible to actually have a CPE that has IPv6 because it's a new one for a new customer. It's not about replacing something that already exists. It's about building a device, a new device for those new customers. So in this mode of thinking, you can have this IPv6 CPE, but you still don't have a v4 service because you're running out of v4 addresses. So the idea is to say, okay, like John Current hinted at this morning, all you have is v6. Okay, you give v6 address to the CPE, and the v4 traffic that comes out for users is simply going to be encapsulated over IPv6. So think of IPv6 as this big layer 2 network, layer 2, layer 2.5. You can think about MPLS for the home, or Ethernet for the home, or ATM for the home, whatever you like to call these things. That's going to carry those IPv6 frames from the CPE to this large NAT, carrier grade NAT, or AFTR, there are multiple names for that, that is going to share IPv4 addresses, not among the 5 devices that you have in your home, but maybe among maybe 100 customers or more. So this is what DS-Lite is all about. So this requires a new CPE. No difference from the other technologies. What the difference is in the way this is supposed to be deployed. This is supposed to be deployed for new customers, and for new customers, you give them a new device. So it makes more sense to give a new device that does this new functionality rather than replacing an existing device. So an alternate solution is to say, what about simply giving v6 only and translating v6 to v4? So Tony explained that translation from v6 to v4 is more difficult than translation from v4 to v4. And that's very true. But that's not the only problem. The problem is that this type of service only works if all the nodes in the customer network are IPv6 capable. And not only all the nodes are capable, but all the applications are v6 capable. So if you remember the chart, the score chart that Dave Ward showed this morning, was showing, okay, devices, Windows 7, okay, Safari, Firefox, all those things are v6 ready. But when you go to the applications, things like online games, things like Skype, no. So if you have any of those applications that are running on a v6-ready operating system with an IPv6 connection to the internet, it will simply not work. So in most cases, this is a non-starter. It's only a viable option if you can guarantee that every single host and every single application will be IPv6 ready. So if you have a cell phone, and it's a feature phone, it has a very limited set of applications running on this cell phone, that might be a reasonable assumption. Now, if you have a phone that is a smartphone, where there is an app store where you can download the application, and maybe there's some differing possibility where your phone becomes a Bluetooth access to a computer, or the phone becomes a local Wi-Fi access point so that any of your local computers can use it to go to the internet. Well, this wireless operator maybe can make assumptions on what are the applications running on the phone, but certainly cannot make any assumption on the application that will be running on the PC connected to the internet via the phone. So this IPv6 only model is not going to work in those cases. So in the end, what works today is to look at the reality that you have IPv4 only application, and those applications are going to be there for a long time. You have IPv4 only devices that are going to be there for a long time. So providing a v4 service one way or another is necessary. That's why Dave this morning talked about having some NAT. v4 NAT is going to come with any type of IPv6 deployment. Of course, the more v6 deployment there will be, the less traffic will go through the NAT. So if you offer v4 and v6, sometimes the question I had is, if you have v4 NAT, why do you even care about v6? Well, the reason is, if you have a traffic that goes through v6, it doesn't go through the NAT, so you can cap the investment on the NAT infrastructure at a point. If all the big content, things like YouTube, Facebook, Yahoo, and a couple others, move to v6, you may have 50% of your traffic, 60, 80% of your traffic that will be v6. That means that the only traffic that you have to NAT will be 20% of your total traffic, or 10%. And the more content provider move to v6, the more this number is going to go down. So you can cap the investments that you will do in NAT technology. You cannot really go down to zero, because there will be always this very long tail of v4 content that will probably never move to v6. But you can cap it at a reasonable level. So having this form of v4 and v6 is really, really critical. Now, this is all about overlay. Because as I mentioned earlier, going native with both is probably not going to work very far, because if you had enough v4 addresses, you will not need v6 in the first place. So if you look at 6RD, this is a v6 overlay on top of v4. So that's interesting when you add this original v4 infrastructure. And DS-Lite is the opposite. Is when you're building this new v6 infrastructure, you maintain the v4 service by creating this overlay. So I want to make an analogy with a phone system, with a voice system. Back in the 1990s, the data traffic worldwide was a small fraction of the voice traffic. So most of the data was actually being carried over voice infrastructure. It was modem, and it was slow, and some of you may remember that. What happened in the year 2000, 2005 is that we went to a point where the amount of traffic that was carried over the data networks went to the same level as the amount of traffic carried over the voice network. And then it shifted over, because voice was growing only a couple % a year, and data was growing exponentially. So what happened was voice all of a sudden became carried over the data network instead of data being carried over the voice network. You have voice over IP. Well, that's what I think is going to happen with these overlay technologies. Right now, there's very little v6 traffic, so it's carried over the existing v4 infrastructure. The more v6 traffic we are going to have, we are going to reach the equilibrium point where you will have the same amount of v4 traffic and v6 traffic, and then you will see more v6 traffic and less v4 traffic. That's when it becomes interesting to think about this v4 as a legacy technology that will simply be carrying over the current v6 technology. So I have a few charts that try to show in details how this technology works. So this is a case of a PC that is in a home network. I'm not sure if the chart is readable from the back. I apologize for that, but it will be available on the web. So this PC tries to reach a website, let's say nanog.org, and sends a packet. So in this scenario, we have a dual NAT environment. There is a NAT in the home on the CPE, and a NAT in the carrier grade, as a carrier grade NAT in the provider infrastructure. So the packet goes to the first NAT with a private source address and a global destination address. This packet is going to be translated by the CPE, just like today. The only difference is that the source address coming out of the CPE is not going to be a global address, but another private address. It's going to be carried over the provider network to the NAT, and then it will be translated a second time, and the source address will become a public address. So you see that you have two NAT tables and two NAT binding, one in the CPE, one in the carrier grade NAT. If it's a protocol like HTTP, there should not be too many problems. If it's a protocol that requires an ALG, things like RTP, RTSP, some interesting things will happen if there is a bug, if something doesn't work. Who is the customer going to call? And how are we going to debug a situation like this? Because the bug may be in the ALG in the carrier grade NAT, or the bug may be on the CPE ALG. It's fairly complex to debug. But this is, in most cases, going to work. And I know a number of providers who are simply thinking that this is the way they're going to solve the IPv4 exhaustion problem, simply drop a carrier grade NAT in the middle. In this chart, I show exactly the same thing, but with a NAT 6.4 instead of a NAT 4.4, a couple of NAT 4.4. So in that case, the packet goes from an IPv6 address, here 2001 colon something, and goes in the end to the same destination. So this packet will go over the v6 infrastructure to the NAT. That is going to create a v4 packet. What you see is the v4 packet that goes out of this NAT is exactly the same v4 packet that was coming out of a carrier grade NAT in the previous chart. Exactly the same thing. And the point I'm trying to make here is that you deploy NAT 6.4 or NAT 4.4, at the end of the day, this is NAT. So the amount of v4 address that you are going to need is exactly the same. The type of breakage that you are going to experience are exactly the same. The amount of resource that you are going to have to deploy to manage those NAT is going to be exactly the same. The only difference is that in case 1, there are 2 NATs. In case 2, there were only 1. No, sorry, in this one, sorry, there are 2 NATs. In case 2, there's only 1. So that may be a minor difference, but in this case, this is a red path, meaning it's an IPv4 path. In this case, this is a blue path, it's an IPv6 path. That's the only difference. Going through the internet after that, this is exactly the same NAT. That's another example with DS-Lite. So in this case, the PC sends this v4 packet toward the same web server. So it's a red packet that goes out, arrives to the CPE, and the CPE is not going to translate anything, simply going to encapsulate into IPv6. So this red packet gets inserted into a blue packet. So the red packet is untouched, unmodified, put into this v6 packet, and in v6 packet, the source address is the IPv6 address of the CPE, and the destination address is the v6 address of the NAT. So this blue packet is going to go through the access infrastructure that is v6, go to the NAT, being decapsulated, and then being NATed. What comes out of this box, again, is identical to the previous case. meaning, once again, I need exactly the same number of IPv4 addresses. I need to spend the same resources managing the NAT, et cetera, et cetera, et cetera. The way it works is that, because everybody has the same local private IPv4 address, so you need to be able to disambiguify this. Well, this is a little bit the same as VRF, where you have private routing tables. Now you have a private NAT binding tables. So the NAT binding table has the v4 private address, v4 source port, and outside the 1234 global address. But this is indexed with the IPv6 address of the CPE, because every CPE has a different IPv6 address, so that's a unique index. So the combination of a non-unique local address, v4, plus a unique v6 index becomes unique. So that's how this technology works. There's only one NAT, so as I mentioned earlier, it's a little bit easier. But once again, at the end of the day, this is NAT. So for those three cases, either the packet arrives, like in this case, a v4 encapsulated in a v6, or in this case, it's a v6 packet arrives and being NATed in v4, or in this case, it has been NATed a couple times. But at the end of the day, it's a NAT is a NAT is a NAT. And that was a diagram with 6RD, where what you see in the middle in red is the v4 access infrastructure. You have this new v6 CPE. And if you compare this diagram to this diagram, this is just the exact mirror image. What was blue in this one becomes red, and what was red becomes blue. Just an encapsulation. So, putting all this together, what does it mean? Well, I think we can essentially identify three different stages here on this evolution. Stage one is for providers who have a v4 existing infrastructure, and what they want is to offer v6 as quickly as possible, as cheaply as possible, because frankly, they don't have any money to invest on this. So creating this overlay of v6 on top of v4 is a very interesting solution. The problem is the CPE. You have to find CPE that support this technology. Stage two is, okay, they now decided that v6 was important enough and they really want to deploy natively IPv6 because that's the right thing to do. So they can deploy gradually v6 where it makes sense. And maybe for some providers that in large areas, or dense area like the Bay Area or Washington, DC, or other places like that, it's viable to do that. There's enough customers. But in some other rural areas, it may not be feasible. So there might be a coexistence of this tunneling mechanism with the native deployment. And the third stage is, going back to my analogy with the voice phone systems and the data system, is when you say, okay, from now on, we build only the new networks using IPv6, and the IPv4 is treated as a legacy service that is tunneled. So in this case, you have this dual stack light technology, or you can even think about NAT6.4 as somehow similar when you know that the end device and the end application can use v6. But the point is that all of those technologies, and I'm essentially echoing what Tony was saying earlier, all those technologies can exist and coexist at any point in time in a service provider, because there may be some areas where they have some new service and they decide, okay, we are going straight to v6 because we know we cannot build it with v4, and then we will overlay v4 on top of it. And the same provider may have some legacy DSL environment where they don't want to invest much money, and they're going to do this 6RD stuff there. So expect to see all this put together. I've mentioned CPE a number of times in this presentation, and I'm going to mention one more time. This is the key. People pointed out earlier that, oh yeah, if you buy a CPE today from the electronics store, does it do v6? The answer is, yeah, well, maybe. And that's a bit of a problem. What does it mean to be an IPv6 CPE? Well, you need to have IPv6, of course, but you also need to have the other technologies like DS-Lite and 6RD, because it might be that the CPE will be used in an environment where this particular provider has decided that 6RD is the way to go. It may be in a couple cities down the road, they will have native IPv6, so they need native, and in another part, in bigger city, they may have decided to go with DS-Lite. So if you are a CPE vendors, you have to put all those technology together. So I wanted to conclude this presentation by talking about some new technologies that we are defining at IETF right now. It's called PCP, for the port control protocol. The problem with NAT most of the time is that you cannot receive incoming connections. So sometimes it's seen as a security device because it protects you, kind of firewall protects you from the outside, but at the same time it prevents you from doing things and like offering services on your computers. So if you want to run a web server on your computer, most of the time today what you do is you go to the web interface on your NAT box and you do port forwarding, like port 80 coming out of the external IP address of a NAT box is going to be forwarded to port 80 on this 192.168.1.2 machines where I run my own web server. Or you do that also for webcams and things. I can do that. I'm sure that most of you can do that. My father cannot do that. So there's a protocol called UPnP. Apple has a variation of this called NATPnP that does this automatically, send a message to open up a pinhole on a NAT. Well, both protocols have some security issues and do not really scale in a service provider environment. They work well in the home, but they don't scale much when you are sharing connection with other customers. So in the IETF, we've started this new effort in this new working group to create a protocol that will enable an application to go and reserve a port. So the semantic is you want to have a server, an XYZ server, and you want to receive incoming connection. So you're going to send a message to the NAT, essentially saying, hey, that's me, I'm here. I need to have a binding of an IP address and a port number. I don't really care what port number it is, because honestly, I can't. My address is going to be shared with many customers. I cannot get port 80, because everybody will want port 80. So you have to be a little bit more flexible here. Says, give me a port. I don't care which one. So this NAT is going to tell you, OK, I can give you port number 6080. And you can use it. So attach an IP address 1234. So any packet that will come to me, to the NAT, so IP address 1234 on port number 6080, I'm going to forward it to you, either through the tunnel or through normal routing, v4, v6. I'm just going to forward it to you. So that's quite interesting because you can also negotiate a lifetime. You can say, I want this port for the next 48 hours. And the NAT can say, no, 48 hours may be too much. Maybe I can give it to you for 12 hours. During those 12 hours, you know that this port is for you. You don't have to send any kind of keep alive messages. Because today, what's what happened? You have some protocols like stun and turn that do things like that, but they don't really cooperate with the NAT. They just try to get around, and every 30 seconds, you need to send a keep alive message. In wireless networks, sending keep alive messages every 30 seconds is very expensive. It takes a lot of spectrum. You send packets that are useless, essentially, every 30 seconds, so that takes bandwidth and spectrum. And B, well, your phone has to be alive every 30 seconds to send this packet. It has to wake up, so it cannot really go to sleep for too long. And that drains the battery. So instead of having a battery that only lasts 12 hours, if you don't have to wake up every 30 seconds, maybe your battery could last 24 hours or 48 hours or something like that. So that's why this is very interesting into wireless networks to do things like that. So in the home, this is how this will work. If you have a new application that's adapted to do that, we'll send a message, PCP message, maybe to the CPE or straight to the ISP NAT, saying, I need a port, give me a port. and the NAT will respond, this is the port I'm going to give you. So the application may say, oh, I would like port number 5002. NAT may say, yes, it's available, or it may say, no, 5002 is not available, but I can give you 7002. And what you will have to do is to find an out-of-band mechanism to tell the people who want to talk to you, I'm available there at IP address 1234, port number 7002. The good news is that those things already exist. If you look at a peer-to-peer client, what a peer-to-peer client does is when it wakes up, start on, it's going to go and register to a tracker. It's going to register to a tracker saying, I'm reachable at IP address X, port number Y. You can use exactly the same thing. So you will send your PCP message, negotiate your IP address 1234, port number 7002, and then you go to the tracker and says, if you want to contact me at IP address 1234, port number 7002. There are very similar techniques if you use a web server, where you can use a redirection engine to say port 80 is actually redirected to port number 7002. So this is the way that I think that applications are going to survive and evolve in this brave new world of NATs, carrier-grade NATs, IPv6, where they will have essentially to negotiate that they want to receive connection from the outside, or they want to send traffic for a fairly long time, a fairly long duration, and they will use this protocol or some evolution of it to say, okay, I'm here, I want a port, negotiate with the network that they can access this. So, that was all I had for today. If there's any questions, I'd be happy to take them now. True. The CPE is a major cost for a broadband provider. But even if I upgrade my CPE to IPv6, my little webcam at home that does IPv4 is not upgraded. My point-and-shoot camera that has a Wi-Fi attachment to push my pictures directly to Flickr or any other social network is not upgraded. My 50-inch TV that has a Netflix client is not upgraded to v6. So even if I change the CPE, all the devices in the home that today are v4 will remain v4. So changing the CPE is a necessary step. It's not a sufficient step. Well, a NAT 6.4 is a carrier-grade NAT, as I just pointed out.
Yes, but
and if I have a NAT 6.4...
It's that double NAT that really scares me. And that
Correct.
For things like port knocking and any of those types of things. I guess CPE is the one that really seems kind of unnecessary. It seems like you've got other ways of getting v4 traffic to the ISP over a v6 link. And you've already changed out the CPE, so you can get that v6 link that's leaving your customer premises and the ISP. Why bother?
So that's a scenario that you're talking about where you take your v4 traffic and you tunnel it over the v6 infrastructure. So in that environment, the address is going to be shared among multiple customers, maybe 100, maybe 1,000, something like that. And let's say that now you have this webcam at home that you want to watch when you are away because you want to, I don't know, check that you locked the door, something like that. You need to access this. How are you going to do that? you need to be able to send a packet to this webcam. So this webcam needs to establish its presence outside. And that's what PCP is all about. So you can think of it as this is for incoming connection. Question?
Yeah, so how intelligent do the applications need to be involved with PCP?
So I couldn't hear you.
How intelligent do the applications need to be for PCP?
It depends. I know, for example, that on a macOS platform, they use a protocol called NAT PMP, and that does things like that with a local home NAT, and that's how they do back to my Mac and technology like this. And the application essentially doesn't need to do anything. Everything is taken care of by the operating system. So there are some other operating systems where it is not the case. Essentially, the API, if the operating system doesn't do it for you, the API is, I want a port, give me a port, and then I'm going to use this port. So if you look at an application today, a typical application, if you look at the C code, is going to do, well, an application will want to receive a connection. It's going to do bind to a socket, and in the bind call, there will be the port number it wants to receive a connection to. So we're going to go from this to a first API call to PCP saying, give me a port and an address. And then in the bind call, I'm going to specify this address and this port number, and that's it.
So does it need to be agent on the operating system that handles communications in that device that's out there somewhere in the file?
It could be done like this. That's what the Mac platform does. Or it could be rolled into a library. Or it could be done inside of the application. So think of it like DNS. Some applications build their DNS packets and send the DNS packets outside, receive the response. Some applications use a stub library, a stub resolver library to simply do an API call, and the library does the rest. Some applications simply call a system, make a system call, and that's the OS that does it for you.
So the operating system receives that understanding this out to negotiate for.
If it's implemented by the OS, yes. If it comes as a library, no. So the library will do it for you.
So there's no operating system to do that now?
Correct. No. The Apple operating system does something similar. And the people from Apple have said that as soon as the standard will be done, they will update it so that it will do that.
Not Windows or...
There is no official commitment from Windows that I have heard of. But this last part is really work in progress that we started something like, I don't know, 4 or 5 months ago. Questions? Okay, well, thank you very much.